Steel is basically the skeleton of our modern world, but it has one major weakness, a real Achilles heel, rust. So how do we protect these massive steel structures from just crumbling away? Today, we're diving deep into an industrial process that's both incredibly harsh and honestly kind of beautiful. I mean, really think about the size of this problem. We're not talking about a rusty old garden gate here. We need a solution that can wrap gigantic beams and super complex shapes in a suit of armor that's going to last for a lifetime. And the answer? Well, it's a lot more dramatic than you might think. The answer? You plunge it into a giant vat of molten metal. Yeah, you heard that right. This whole process is called hot dip galvanizing, and it's this amazing fusion of raw chemistry and just brute industrial force. Now, it is so important to understand this. This is not just a fancy coat of paint. Hot dip galvanizing doesn't just sit on top of the steel. It chemically bonds with it. It forges an entirely new, incredibly resilient surface. So how does this all work? Well, our journey is going to take us through 5 key stages. We'll start with the crucial prep work, then the fiery dip itself. We'll look at the science of how that armor is forged, see what happens when things go wrong, and finally, look at the final test that proves its strength. Okay, before a single piece of steel gets anywhere near that zinc bath, it has to be immaculate. I mean, perfectly clean. Any little bit of dirt or rust or oil will totally prevent the zinc from bonding, which makes this preparation stage absolutely critical to the whole process. It's basically a 3-step cleaning marathon. First, pre-cleaning gets rid of all the obvious surface grime. Then, it gets a dip in an acid bath, that's called pickling, which strips away any rust and that tough mill scale. And finally, a flux bath takes care of any leftover oxides and puts on a protective layer so new rust doesn't form right before the big plunge. So with the steel perfectly clean, it's time for the climax of the whole show, getting submerged into a massive vat of molten zinc, which is known as the galvanizing kettle. And when we say hot, we really, really mean it. The zinc is kept at a searing temperature, somewhere between 820 and 860 degrees Fahrenheit. This extreme heat is the engine that drives the whole chemical reaction between the zinc and the steel. You see these huge structures, like this I-beam, being carefully lowered right into the kettle. And that kettle is filled with at least 98% pure molten zinc. That's to make sure every single surface, every nook and cranny gets completely covered. You know what's amazing? For most things, this whole dip lasts less than 10 minutes. In that tiny window of time, the intense heat triggers a reaction that literally fuses the zinc to the steel. After it's pulled out, the piece is cooled down, and that locks the new protective coating right into place. So we've seen the process, but what's actually happening at a microscopic level? To really understand why this armor is so effective, we need to zoom in and look at the how, the exact molecular changes that just happened in that fiery bath. This is the crucial point right here. Galvanizing is fundamentally different from paint. Paint just kind of sticks to the surface. Galvanizing creates a series of brand new alloy layers. They're part steel, part zinc. It's a true metallurgical bond, which makes the coating an actual part of the steel itself. This incredible strength comes from a layered structure. Think of it like an onion. Starting from the steel base and moving outwards, the reaction forges these distinct alloy layers. First, you get the incredibly hard, iron-rich gamma layer. Then, the delta and zeta layers, which have more and more zinc. And finally, the outer surface is the eta layer. That's pure zinc, and it serves as the first line of defense. Now, this process is super robust, but it's not foolproof. Imperfections can definitely happen, and understanding them is key to making sure you get a quality product. So let's play detective for a minute and look at some of the common defects. A lot of problems can be prevented before the steel even gets to the factory floor. Good design is just so critical. You have to have holes for the molten zinc to flow in, and just as importantly for it to drain back out. Without them, you end up with these pools of zinc and even totally uncoated spots. Here's a classic defect. See those thick drips and all those uneven surfaces? This is what's known as runs and lumpiness. And obviously, it messes with how uniform that protective coating is. The cause here is usually about process control. If the steel is pulled out of that zinc kettle too quickly, the extra zinc just doesn't have enough time to drip off properly. Or, on the other hand, if the bath is a little too cool, the zinc is thicker, less like water, and you end up with the same lumpy result. Okay, this one looks pretty nasty. It's called a flux inclusion. That rough, kind of bare-looking patch you see, That's where the pretreatment flux got trapped underneath the zinc layer, and it physically stopped the zinc from bonding with the steel. And this is a perfect example of how critical that first cleaning stage really is. Any failure in the fluxing or cleaning steps is going to lead directly to a defect just like this. The zinc simply cannot bond to a surface that isn't perfectly prepared. So after the steel's been cleaned, dipped, and cooled, how do we actually confirm that the armor is ready for battle? Well, that's where the final inspection comes in. Inspectors have a very clear checklist. First, a really thorough visual check for any of those obvious defects we just saw. Then they use these special magnetic gauges to measure the thickness of the zinc coating to make sure it's thick enough to provide protection for decades. And finally, they test to make sure that coating is really truly bonded to the steel. And these checks aren't just someone's opinion. To make sure that a bridge in Japan is just as safe as a skyscraper in New York, the entire process is governed by these strict, internationally recognized standards from organizations like ASTM and ISO. These are the global rulebooks for what good looks like. And these rulebooks are incredibly detailed. They specify everything, from the exact chemical wake-up of the zinc bath to the minimum coating thickness you need for different types of environments. They even define what a good finish looks like and spell out the right way to repair any damage, all to ensure consistency and safety no matter where you are in the world. So, we'll leave you with this thought. The zinc coating is literally designed to corrode first. It sacrifices itself over decades to protect the steel underneath it. It's a fascinating idea, right? So, what other materials can you think of in our world that are engineered from the start to be their own bodyguard?